Okay, section 24.8. This is the second video about that. We're going to look at the diazonium methodologies that we can make use of here to do some very interesting synthetic chemistry. So, diazonium chemistry. The first thing we're going to learn is diazotization. So we can take an amine and we treat this with H2SO4. Now watch carefully. HNO2. Notice the 2, not 3. If you put 3, it's wrong. It doesn't work. Okay? Now what this does is it converts the benzene ring into a diazonium. So this is diazonium. Of course, what you, I think, will immediately recognize is there's a very stable molecule. It can lose that, and we can do substitution chemistry, and that's one of the key things that we're going to see with this compound. So that's how we do diazotization. Now, what can we do with this? Of course, there's a counter ion here. In this case, it's HSO4 minus. But we can control that by changing the acid. So if we use HBF4, which is a very common example, then we would have the BF4 counter ion over here. And that one is useful in some places. For instance, in making the fluoride compounds. All right, so if we have the diazonium compound, what are we going to do with it? So here's B. So the first of these is what's called the Sandmeyer reaction. Meyer. In the Sandmeyer reaction, we take a diazonium salt now we want to pick X so that it has the proper anion. It is the proper anion. So for instance, we're going to learn that in the Sandmeyer reaction with copper X, where X equals chloride or bromide or cyanide, we can couple these. So you don't want the diazonium bromide if you're going to use the copper chloride to try and do the chemistry, because then you're going to get a mixture of halides, because the halides are going to all mix. So if you're going to use copper chloride, you would want to use hydrochloric acid in the synthesis of your diazonium salt. So I'll add that up here. You know, you can use HCl, you can use HBr. BF4 bisulfate, those are not going to interfere in the chemistry that we're doing here. The mechanism of this is complex. It's believed to be a mixture of carbocation formation at the diazonium. Of course, this can happen and you can get the carbocation there because you lose dinitrogen, a very, very stable molecule. And then whatever X is acts as the nucleophile. And it goes in exactly the same place. So I'm going to put R here, but R can be all sorts of different kinds of substituents all over the place, almost all the things we've dealt with before, but just as a placeholder so you see that X ends up wherever we started this diazonium from. And that's important because we don't get mixtures with this. This is one way that we can avoid producing mixtures of compounds, is to use diazonium chemistry. And in fact, it's used widely on large industrial scales to make, for instance, azo dyes we'll see in a few minutes. So let's just take a quick example here. If we have the methyl diazonium tetrafluoroborate, and we react that with copper cyanide. Now notice this is copper 1, okay, copper 1. Copper 2 doesn't work, you need copper 1 because, as I said, this is a mixture of carbocation and radical chemistry. We're not going to worry about arrow pushing for this. Then you can get substitution of the diazonium. In this case, since I used copper cyanide, it produces the copper cyanide, or the cyano compound. So this makes a carbon-carbon bond. Of course, we can make carbon-halogen bonds and other kinds of bonds. So this is very useful chemistry. But what about iodide? Well, turns out that we can do this chemistry with iodide, but we need a different nucleophile. What we need here is simply sodium iodide. Okay, iodide pretty easily forms radicals, so it's not too big a challenge to get this chemistry to occur. And so the product here will be the iodide. So for iodide, all you need is sodium iodide. So that's 1, 2, 3, 4 new chemical reactions that we've learned here. And then let's add another to that. There are 2 more that we want to learn with this chemistry. So I'll call this C, hydroxylation. We have a special set of conditions for that to occur. So there's our diazonium, and we are going to react this with copper 1 oxide. Okay, again, notice the oxidation state. It's Cu2O, so that means it's copper 1 oxide. This is reacted with copper nitrate. We would say that's cupric nitrate because that's copper 2 in water. And with that, we can successfully substitute the diazonium for a hydroxyl. That's very powerful chemistry there. Phenols have lots and lots of applications. All right, now there's one more that we want to do with these diazoniums in terms of the simple substitution chemistry. So all this is a direct substitution. Now it's not a nucleophilic substitution like we've seen before. It's not electrophilic substitution. right? We're not replacing hydrogens and we're not replacing halogens, we're replacing this diazonium. So N2 is probably considered the best leaving group. Maybe if we could make an argon one by some nuclear chemistry, that would be better, but that's about the only thing that would be better. All right, so what would be really useful would be to convert the nitrogen, the diazonium, to a hydrogen. And it turns out there is a good methodology to do this. So again, placeholder with the R substituent there. The reagent that we need here is hypophosphorus acid, so H3PO2. It's not H3PO3, it's not H3PO4, it's H3PO2. It's very different than phosphoric acid. So let me draw the product here first. So we put the hydrogen there. Now, why is it that this works? Hypophosphorus acid has the following structure. It has phosphorus hydride bonds, and so the phosphorus donates that hydrogen. Alternatively, it may be extracted by the radical that we produce. So this is very useful, and we'll see this in just a few minutes in terms of applications, because it means that we have a silent directing group. Okay? So we have to begin to see things that aren't there. We're going to see chemistry in a minute where the directing group effects from electrophilic chemistry won't make sense. It doesn't seem that we could make this product. And it turns out that's going to be our key to recognizing diazonium chemistry. That is, to seeing the functional group that has been removed and replaced with hydrogen. And so we can get what appear to be directional effects that don't make sense for simple electrophilic aromatic substitution. So there's one more reaction that we need to learn here. This is the diazonium coupling reaction. So the diazonium is really electrophilic. So we would have a formal plus charge on this nitrogen attached to the carbon. Of course, it has a counterion there. We can react it with very nucleophilic arenes. So in particular here, when Y equals OH, the phenol, or an aniline derivative, not an amide, but an aniline. So the nitrogen needs to be attached to the ring, and R is an alkyl, or could be aryl groups there. So when you've got a lone pair in this strong position, remember this resonance form where you can attack at the para position. So I'm kind of sneaking in a bit of mechanism here. Now, how many arrows? 1, 2, 3, 4. Again, this is an example that's more than 3 that proves our rule. It's because of conjugation that we have more than 4 arrows here, so we can see all the way back where the electrons would start pushing from. Now, what this will yield And again, it requires these strongly activating hydroxyl or nitrogen, so phenols or aniline derivatives. And it produces the para product. Put Y here. These are called azo compounds or azo dyes because they were used in the dyeing industry, and they're still used in many cases today. Not in all cases. In many cases, modern dyes have been prepared that are more stable or that stick to fabric better, and with all the synthetic fabrics that we have out today, there are other things. But this was a huge part of the dye industry, cloth dyeing industry, the fabric and clothing industries in the 1800s and 1900s. All right, so those are the chemistries of diazonium compounds. Now this is like the introduction to electrophilic aromatic substitution. You've got to know these, about 7 different kinds of reactions. You just have to recognize them. So go to your textbook, practice specific examples of each of these, and learn how to recognize them. Next, I'm going to show you how to put this together to make some very interesting compounds.